Okay, welcome back. So what we're doing in this video is looking at the SACE Specialist Mathematics Exam from 2019, and we're doing question 10. Okay, so question 10 was a modelling question where we were looking at a differential equation, which is the logistic equation. So the question reads, scientists can study the growth of the world's population using mathematical modelling. For one model, the rate of population growth since the year 2000 is given by the differential equation there, which is the logistic equation, and it's saying that the time rate of change of n is proportional to 0.002 times n, all multiplied by 12.5 minus n, divided by 12.5. Okay, n is the population of the world in billions at time t, in years since 2000. Okay, so the first thing that we're asked to do, this is question 10a part 1, is to show this partial fraction decomposition. Okay, this is similar to question 1, where you're given the decomposition, you just show that it's true. And again, as I said when I did the video for question 1, these sort of questions are easiest handled going from the multiple fractions to the single fraction. So that's what we're going to do here as well. We'll start from the right hand side, and that's 1 over n, and to get the denominator that we want, we need to multiply this by 12.5 minus n over 12.5 minus n, and then we're going to add on 1 over 12.5 minus n, and then this has to be multiplied by n on n. So those two things that we've multiplied by are just equal to 1. We haven't changed anything, but we're going to end up with a denominator where that denominator is going to be n times 12.5 minus n in both cases. So we'll put it on the single fraction here, and in the first case we're going to get 12.5 minus n, and in the second case we're just going to get n, and you can see the minus n and the plus n cancel, and so we're left with 12.5 divided by n, 12.5 minus n. Okay, that's all we needed to show. That was the 1 mark. That's equal to the left hand side, and so that's job's done. All right, now part 2, we want to solve the differential equation with the initial conditions and show that we can come up with a solution with n as a function of t. Okay, so what we would do is, starting with our differential equation, just recall what the differential equation was. It's this thing back on the start of the question. We've got 0.002 times n, and that's equal to dn/dt. Okay, so let's write that at the start, just so it's all on the one page. And then it's 12.5 minus n all over 12.5. Okay, so we're going to separate these equations. So we want the n terms on the left-hand side, and we'll leave the 0.002 on the right-hand side and make that the t side of the equation. So the n side of the equation is going to look like 12.5 over n, 12.5 minus n, so minus there, dn, and that's going to be equal to 0.002 dt. So that's separated, and we can use the result from the previous part to break that fraction on the left hand side down into 1 over n plus 1 over 12.5 minus n. dt. On the right hand side, 0.002 dt. Okay, so now we can integrate. And when we integrate, what we're going to get is some logs of the absolute value of the things on the denominator. So the first term will be a natural log of the absolute value of n, and the second one will be minus, because it's minus n on the denominator, and it's the natural log of 12.5 minus n. Okay, the right hand side we're going to have 0.002t. We integrate 1, we just get t. So if we integrate 0.002, we get 0.002t. And we're going to have a constant of integration c. And at t equals 0, we have that c, we have n. Let's get rid of that c. We have n is equal to 6.08. And so substituting that, we get that ln 6.08 minus ln absolute value of 12.5 minus 6.08. That's what c is equal to. And we can write that in terms of c is equal to ln, and these are both positive numbers, so we don't need the absolute values anymore. And we're going to get 6.08 divided by 12.5 minus 6.08, which is 6.42. Okay, so we've determined what c is, and so we can write our equation by putting the logs together. We've got ln absolute value of n divided by 12.5 minus n. Okay, because we've got two logs that are subtracted, we can write them as a quotient. And then we move the c from the right hand side to the left hand side, we'll get minus ln, we don't need the absolute value sign, 6.08 over 6.42, and that equals 0.002t. Okay, so going to the next page now, we'll put that log all together in the one term, 6.42n over 6.08 times 12.5 minus n, 0.002t, and now we can raise everything to the power e. Okay, and raising everything to the power e gets rid of the log on the left hand side. And so we can write this as 6.42 over 6.08 n divided by 12.5 minus n, and that's equal to e to the 0.002t. Now we want to make n the subject of the equation, so we're going to have to multiply the 12.5 minus n to the right hand side, and while we're at it we can put the exponential term on the left hand side. The reason why we're doing that is because there's just an n there by itself. This is going to work out. So we'll move that to the left hand side. We're dividing by the exponential, so there's a minus that goes in, and the right hand side now is just the 12.5 minus n that we took from the from the left hand side. Okay, now we can take the minus n that's on the right hand side, bring it over to the left hand side, and then we've got all the n's on the left hand side. So the 1 from the right hand side will give us a 1, and then we've also got a 6.42 over 6.08. Hang on, close that parenthesis too soon. And on the right hand side we've got just the 12.5 that's left. So the last thing we need to do is just divide through by that term in the parenthesis, and that will give us that n is equal to 12.5 divided by 1 plus 6.42 over 6.08 e to the minus 0.002t. Okay, so that's pretty much all we needed to do. The last thing that we can just check is that when we get 6.42 and we'll write this as an NB, 6.08, that's equal to approximately 1.06 to 3 decimal places. And so to 3 decimal places we can write n is equal to e to the minus 0.002t. Okay, which is exactly what we wanted to show according to the wording in the question. Okay, so that's solving the differential equation. That's really the hardest part of this question. Now, these next couple of parts are just a couple of marks for doing a few more things. One is part B. According to this model, what is the year that, in what year, sorry, is the population growing at its greatest rate? Okay, well, this is, if we look at dn dt, this is the rate that the population is growing. It's the rate of change of the number of people against time. And we can see that that is proportional to n and 12.5 minus n. So that's how the growth rate depends on n. And so if you were to draw a quick plot of that, showing growth rate against n, what you would have is it equals 0 at n equals 0. It also equals 0 at n equals 12.5. And at 6.25, n equals 6.25, it's not a maximum because it's a parabola. It's a quadratic expression. And this is the point where it's got a maximum value. So it's easy to see that the maximum at n equals 6.25. Okay, so we don't know the time that n is dn dt, sorry, is a maximum, but we know that the n at which dn dt is a maximum. So what we need to do now is solve our equation to find out what t is. Okay, so we've got 6.25 is equal to 12.5 over 1 plus 1.06 e to the minus 0.002t. We want to solve that for t. Okay, and so what we can do is multiply through by 1 plus 1.06 e to the minus 0.002t and divide through the 6.25. And if we do that manipulation, what we're going to end up with is 1 plus 1.06 e to the minus 0.002t. And on the right hand side, it's 12.5 divided by 6.25 is just 2. And then we can cancel the 1 off with one of these from the 2, and that will bring us to a 1. And then what we can do is multiply the e back over to the right hand side, and when we get e that becomes positive, then 0.02t is equal to 1.06. We can take logs. 0.002t is equal to the log, well, I should write ln to be consistent, 1.06. And so t is equal to basically 500 times the log of 1.06, which is approximately equal to 29.1. Okay, so that's in years since the year 2000, so year is 2029. And it's in fact around 0.1 into that year. Okay, so it's sometime in February. Okay, now according to this model, what is the limiting value of the world's population? Well, as t goes to infinity, if we look at the solution, if we go back here, say, and look at the solution that we've got down here, you can see the denominator, as t goes to a large number, this term will go to 0, this whole term here will go to 0, and the denominator will go to 1. Okay, any positive value of t, this will actually be a little bit more than 0, so this will be a little bit more than 1, so n will be a little bit less than 12.5. But as t goes to infinity, n is going to go to 12.5. So let's get the pen back. So n goes to 12.5. So that's the limiting value. Of n. Okay. And that's basically it. Okay, so that completes this video. It also completes the series on part as far as booklet 1 goes. So there's still 5 questions in booklet 2. These are the longer questions, but this completes the shorter questions that are in booklet 1. All right, thanks for watching. If you liked the video, then click the like, and if you've got any comments or questions, make a comment or question below. And if you want to hear about new videos as they're coming out, then don't forget to subscribe to the channel. All right, thanks very much. Until next time, see you later.